10.1, using properties of tangents. We're going to learn about tangents as well. So we'll determine if a line is tangent to a circle using some theorems and properties and find missing information if we are given a tangent. So let's look at some vocabulary first. So first of all, the circle is a set of all points in a plane that is equidistant from a given point called the center of the circle. So we kind of already know what a circle is, but it's the set of all points that are equidistant. And there's an infinite number of points. And all the infinite points make up the circle. So the radius, which you are familiar with, is the segment whose endpoint is the center of the circle, and the other endpoint is on the circle itself. And it's the distance from the center to any point on the circle. A chord is a segment whose endpoints are on the circle. So chords don't have to be through the center, although they can, and if they are, they will be a diameter. So here's a chord right here. So it has endpoints on the circle. And a diameter is a special chord that passes through the center of the circle, and it's the distance across the entire circle. So it's really twice the radius, which you are familiar with that as well. And here's some additional vocabulary. We have a secant line. So basically a secant line is just a chord that it's extended. So you have the original chord, and then when you extend the chord, you get a secant line. And then the tangent line is a line that intersects a circle in exactly one point. And that point is called the point of tangency. So there's our tangent line. And again, we call that point, the point of tangency. So we also can talk about coplanar circles. So two circles can intersect in 2 points. Here's what 2 points of intersection look like. They can intersect in 1 point or no points. Coplanar circles that intersect in 1 point are called tangent circles. So these are our tangent circles right here when they intersect in 1 point. Coplanar circles that have a common center are called concentric. So these circles are called concentric circles because they have no points of intersection, but they have a common center. That's what that would look like. So we're going to talk about what's something called a common tangent. A common tangent is a line, ray, or segment that is tangent to 2 coplanar circles. That is called a common tangent. So here's some examples of some common tangents and what they could look like. So let's see if you can match the terminology here. So take a minute to see if you can match up as many of these terms in the vocabulary with an example from the picture. So if we look at point D right here, that's a point on the circle, and that is your point of tangency. So D is your point of tangency right there. There's your line that's tangent. FH right here is this line right here. That's FH, and that is a tangent, a common tangent. You can see it has points on these 2 circles. So that is your common tangent. So let's look at what segment CD would be. Segment CD right here, that is a radius because it has a point, it comes from the center and goes to a point on the circle. So that would be a radius. And AB right here, that is a segment. Notice it's different because it has no line pieces above it. It's just a segment AB, so that is a chord. Point C is the center of the circle. So here's point C, and that is our center of the circle. Segment AD right here. So if we go, I'll use a highlight option here. So if we do AD, that particular segment, that is a diameter. Segment CD was supposed to be going over here. Sorry about that. It was supposed to be going to, I said radius, but I didn't actually be careful enough to put it there. So now we can go ahead and put DH as our diameter right here. Okay, and last but not least, we have AB, the line. So this is the whole line AB that continues, and that is a secant line right there. All right, so hopefully you're understanding this terminology. So we can come to our first theorem, 10.1. In a plane, a line is tangent to a circle if and only if the line is perpendicular to a radius of the circle at its endpoint on the circle. So this line right here, M, will be tangent to the circle if and only if this segment of, or this radius right here, is perpendicular. So line M is tangent to circle Q if and only if M is perpendicular to QP. And by the way, we might not have talked about this, but right here where it's this little symbol right there, that means circle Q. So that means also that Q is the center. That's how we name circles. Or we can use the word, or we can use that symbol. So, in the diagram, it tells you that BC is a radius of the circle C. So this segment right here is a radius. This segment right here is a radius. So BC is a radius of the circle. Determine whether AB, the segment, is tangent to the circle. Well, if it's tangent, then it will be perpendicular. And if it's perpendicular, then you have a right triangle. So if that is the case, this would be a right angle. Right here. So question mark. Well, how do we find out? We use the Pythagorean theorem to see if 7 squared is equal to 3 squared plus 6 squared. This is 49 and this is 45, and that is not equal, so that is not a tangent because it's not a right angle. Okay, so you can do that first one, and then you can check the notes to see if you think that one, AB, is a tangent to the circle. So now it says in the diagram AB is tangent to circle C at point B. So now we know this is a tangent, it is perpendicular. We want to find the radius. So we want to find the radius right there. Well, it's a right triangle. So we can set up r squared plus 12 squared is equal to, but wait, this part right here is 8. But then you have this part, the other part right here is still a radius. So how long is the hypotenuse? Well, the hypotenuse is r plus 8. So now we're going to solve that. We get r squared plus 144 is equal to, and remember, you don't just square r and square 8. This becomes r plus 8 times r plus 8, and this you have to FOIL. If you remember back, what we have to do is multiply the first term times the first term, the last terms together, and then the inside and the outsides. So we multiply all the terms together, all the different combinations, and what that gives us is r squared plus 16r plus 64 equals r squared plus 144. So now we're going to subtract r squared from each side, which gives us our r squareds actually cancel out. So if we subtract r squared, they cancel out. So now I'm left with 144 is equal to 16r plus 64. Now I'm going to continue solving. I'm going to subtract 64, which gives me 80 is equal to 16r. So then divide, and r is equal to 5 units. So my radius is 5 units long. Okay, here's another additional example. It says, suppose a space shuttle is orbiting about 180 miles above the Earth. So what we have here is this is that little orbit right there above the Earth, where d is the distance, what is the distance, d from the shuttle to the horizon. So what we're trying to find here is we're trying to find this distance d right there. So what is that if the radius of the Earth is about 4,000 miles? So this radius right here is 4,000 miles. So again, it is a right angle right there with the horizon. So we can set up an equation that d squared plus 4,000 squared is equal to, and then how long is the hypotenuse? Well, this part of it to there is 4,000. So the whole hypotenuse is 4,180 units squared. So go ahead and see if you can solve that, and then you can check back to the answer key, or the notes for the correct answer. Okay, so the next theorem, tangent segments from a common external point are congruent. So if you have this is a tangent and this is a tangent, and they come from the common external point, this is the common external point right here, that's S, then the segments are going to be congruent. So what that means is this piece and this piece are the same. So if SR and ST are tangent segments, then SR is congruent to ST. So it tells you in this example that JK is tangent to circle L at K, and JM is tangent. So this is a tangent, and this is a tangent. It tells you that, and it tells you that these are the points of tangency. And so then you know that they're both coming from J, the same external point. So then you know that these two are congruent. So then you can just set up 5x minus 4 equal to 2x plus 2. And then when we move things around, we get 3x equals 6 and x equals 2. So all we're asked to do is find the value of x. The second example is very similar. So again, that's your turn to try and see if you can come up with the correct answer. And then check back to the notes to see if you got it correct and